Thank you for having me. Let's switch this one too so I can see. So I'm going to give you both kind of a history of why we created Croquet. I'm going to give a little bit of a deeper dive on why we did it, how it works. I'm going to do some demos. And then I'm going to talk about the deep details of how it actually works, because I think I'll give you kind of a good understanding. And then, depending on the time, I'll do a deeper dive on actual applications that we've built. This is the background of what we did. This quote is one of my favorite. Man is much more than a tool builder. He is an inventor of universes. This was by Alan Kay, who was my mentor, in a paper he wrote, which I consider one of the most important papers in computer history, A Personal Computer for Children of All Ages, where he describes for the very first time the idea of what we think of as the laptop today. So what I'm going to do is, first of all, give you a view of the future through what I call the lens of the past, because how we got here matters a good deal, and understanding where we want to go. These are the people I consider to be the heroes, the true heroes of the computer revolution, the people who created the world that we live in today. I think 1968 is the most important year in computer history because many things converged that year to really define everything that's happened since. And they were really crucial. I'll start with Doug Engelbart. You saw some videos before this that were showing him and others. Doug was a friend of mine from many years ago. He's passed away. He's known as the person who created the mouse, but in fact the mouse was a part of a much bigger system, and that system, when you think about it, the mouse was like the radio on your dashboard. It was a small part of what he was really after. Other things that he's known for, he invented the idea of Windows, hypertext, concept of bootstrapping. I'll talk a little bit about that. And in particular, most importantly to me, was this idea of collaborative computing. So his big idea is collective IQ, all of us being able to contribute and create together, was a crucial concept that actually came from the early 60s. This idea of like, how do we work together to solve very, very large problems? But in doing that, he formed this concept of bootstrapping, and that's the idea is the state of your technology allows you to better manipulate information, which allows you then to improve the technology. So that's actually a spiral, if you want to think of it that way. We're constantly improving. One of the things he's known for was in 1968, he did a demonstration of his ideas that really had a profound, deep impact on computing. This is a short excerpt from that. Hopefully we have the sound here. Hold on. I think we lost the sound over there. I'm going to just turn it back on. Just a second. Oops. I turned my glasses on. Oops, that's the wrong guy. Okay. So it was coming into my hearing aid, so I couldn't hear it.
And so this special thing, if I label 13, will switch over. So in his display, he sees my text. So I'll execute it. And sure enough, it does. But what's that running around? Well, if he's looking at my text, he'd like to have something to say about it. So we put on a marker, a tracking spot that he controls. So he's sitting in Menlo Park looking at this text, and he can point to it. But we've carefully reserved for me the right to control and operate on this. So my bug is more powerful than yours. But we can have an argument. Yeah. That's what they call a bug fight. So, all right. So in case you haven't been listening, Bill, We've been going through lots of examples and setting up in collaboration here so that we can go on into information retrieval. And we've set up now audio coupling, and then we're both looking at the same display, and that'd be very handy to work. We can talk to each other and point, and maybe later I could hand you the chalk on this blackboard, like saying, here, you control it. But let's stay this mode now and add another feature that hardware-wise is available to the kind of display we have. I'd like to see you while I'm working on it. So before I can do that, I have to set up my display in a certain way. Set it up so I see it over like that. That leaves a corner up there, and I say, now computer, do the automatic switching that'll bring in a camera picture from the camera mounted on his console, such as the camera mounted on mine is. Hi, Bill. That's great. Now we're connected audio. You can see my work, you can point at it, and I can see your face, and we can talk. So let's do some collaborating.
What's amazing is they were connected by a microwave connection between Stanford and downtown San Francisco. This is maybe the first video conference, that remote video conference that was ever done. But the more important thing was they were actually sharing that screen, interacting with that screen together as if it was a single system. So what's truly remarkable, it was time sharing. It was online system, was NLS is what they called it. It had 192K bytes. It was a time sharing system, ran at about 1/2 MIP, but it supported 12 simultaneous users, had sub-second response, and is fully collaborative. Those guys really knew how to program. Second, 1968 was also the year that Alan Kay invented the idea of the Dynabook. The Dynabook is really, Alan's known as the father of the personal computer for a very good reason. Part of it is this device. He had worked very closely with Doug Engelbart. He spent a lot of time in his labs. So if you notice that picture of the two children, what's really important about that, first of all, they're both using Dynabooks, but when he envisioned this system, he thought of those two children working together, collaborating. If you look at the screens there, you'll actually see that they're actually playing Space War together. The idea, the original concept of the personal computer we think of today was intended to be multi-user, multiplayer. This is the system that he created with his team at Xerox PARC. This is the Smalltalk platform, really more than just it's not just a language, it's actually a kind of a full operating system. What's really remarkable is it defined almost everything we think of today when we use our laptops or our tablets or even our phones. It was all here. I'm going to just play a very short amount of this, but if I sat you down, 1978, that's I think 45 years ago, you would know how to use this already because you've been using this. Oops, back up. I want to play this.
Is used to select information. A window is selected by moving the cursor inside of it and pressing the first mouse button. A selected window displays above other windows, much like placing a piece of paper on top of a stack on a desk. Information in the window can be selected using this first mouse button. The selected information can be changed. Here, selected text is displayed as white characters on a black background. The selected text is replaced by typing on the keyboard.
I just find that, truly remarkable. That really, I think the most remarkable thing is very little has changed. He set something in motion that we're still part of, but we really haven't made substantial changes beyond that. This is Steve Jobs talking about when he saw that system for the first time.
And they showed me really three things. But I was so blinded by the first one that I didn't even really see the other two. One of the things they showed me was object-oriented programming. They showed me that, but I didn't even see that. The other one they showed me was really a networked computer system. They had over 100 Alto computers, all networked, using email, et cetera, et cetera. I didn't even see that. I was so blinded by the first thing they showed me, which was the graphical user interface. I thought it was the best thing I'd ever seen in my life. Now, remember, it was very flawed. What we saw was incomplete. They'd done a bunch of things wrong, but we didn't know that at the time. It's still, though, they had the germ of the idea was there, and they'd done it very well. And within, 10 minutes, it was obvious to me that all computers would work like this.
And all computers do work that way. So let's go back in time a little bit. Ivan Sutherland is known for many things, but perhaps the most important was the developer of interactive graphics via Sketchpad, 1963. But the other thing that he did was he set the bar for where we should be going. In 1968, he created the first real-time 3D graphics head mount with an ultrasonic tracker. By the way, one of my old boss, was the designer of that ultrasonic tracker, which is kind of cool. So I'm at 1 degree separation from that project, which is very, very neat. 65, he wrote this paper about the ultimate display, and if you're interested in the metaverse, virtual reality, you owe it to yourself to read it, because it's talking about where it will go, not where it is. And I think this is really important to understand the implications and the opportunities. 1965, that's pretty amazing. But here's a video of that system, and what you'll notice is it's not a VR system, it's actually an AR system. 1968, this is kind of, to me, crazy, but here. So he's looking around in a virtual world. It's not a very big one. Today we might laugh at it a little bit, but honestly, it's pretty amazing. That cube, you can walk around it, he's seeing it, he's able to explore that, in this case, simple world. They made much more complex environments later, but that gives you a pretty clear idea of the nature. And notice it's a see-through display. You can see his eyes. They understood where it really needs to go. They're doing 3,000 lines at 30 hertz, which is, at that time, just astonishing. They had mechanical ultrasonic trackers. They had a specialized chip that would do this for them, and really was the very first AR device. So I'm going to now talk a little bit about, I gave you historical concepts where this stuff came from. Now we're going to talk a little bit about the Croquet platform, because it also has a bit of history. This is the team that created the very first iteration. That's me standing next to Alan Kay. David Reed was our other partner, along with Andreas Reed, Rob. David Reed was the architect of the UDP protocol and co-architect of TCP/IP. Alan called him the slash in TCP/IP. His thesis was this concept of replicated synchronized computation that he originally formalized at MIT with the idea of real-time banking transactions. But Alan used to read everybody's thesis and had read that and said, this might be the ideal way for us to create the platform we wanted to do. So we got together and did that. This is actually a demo from 2003, so this is 20 years ago. But this is Alan and me demonstrating the first version of Croquet. So let me do that.
So I'll come in, block, he turned into fish. Okay, so what I'm going to do here is there's not enough fish, I'm going to create my own. So I need to grab a little paint package. And what I'm going to do is literally draw a little fish. Like so. Give it a little bit of an eye. And a little bit of color there. And then paint that. And then what's going to happen here, by the way, is the work of
originally the work of Takeo Igarashi, who's now a professor at the University of Tokyo, was done for his master's thesis, I think, and it's pretty darn cool. Go ahead.
What I just did, this is the fastest and easiest 3D design tool you've ever saw in your life. Wow. Now Alan's going to make something similar. He's going to add a little sequence to it.
Yeah, so I should come over here. I'll do the same kind of thing. I'll go get a drawing tool here, and I'll do a much harder problem for this program, which is what do we call these things? Seaweed? Seaweed. So you can imagine now the system is going to, basically what it has to do is it has to take these planar things that I'm painting and figure out the major and minor axes all over the thing regardless of what it is, and then use those as a way of spinning out the tiling for the thing. So this is, we'll have to think just a little bit here on this one. I couldn't actually believe that this would work. So of course I never even tried to do it. Wasn't it your kid?
Yeah.
Dave has a kid, so here it is.
And it's coming over here. Thing to notice also is everything we make is automatically copied over. So I've got, I'll grab this and move it around a little bit.
Actually, it's not really copied, it's actually recreated.
Right.
Because this is the replication architecture.
So what we've done is a shared, I said earlier, this is a collaborative environment. It's a broadband conference call.
All of these things are scriptable just the way I showed you. I'm not going to do that right now. But basically, it's all scriptable. And while you're in the routine, one thing
Anyway, this, if you saw Doug Engelbart's demo earlier, this is, in a sense, that grown up a bit. So when we started thinking about doing kind of the modern version of Croquet, we were thinking, the advantages we had and why we would do it this way. Tim Sweeney wrote, initiatives to place real-time processing on the wrong side of the latency wall have always been doomed to failure because even though bandwidth and latency are improving, local computing performance is improving faster. This is a big deal. This idea you can't trade one for the other, really. So what's Croquet? You kind of have a sense already. A bit identical synchronized simulation platform. Simulation code is right now written in JavaScript, although Rapier, as I'll show you, if you saw earlier, is written in Rust. The rendering, UI, visual effects, are all managed locally, and I'll talk about this. One way to think about, in fact, the way it is Croquet is a model view controller architecture. Sessions are automatically synchronized between players. When a new user joins, it's automatically shared. This is a really big deal. So why JavaScript? I'm not going to go into too much detail, but JavaScript has certain features. There's a number of languages that share this. It runs exactly the same on every device. Why is that important? That means that if I do an execution of some function or something, some code, some object, it's going to run exactly the same on my phone, on my Mac, on my Windows, any device, my head mount. There are a number of languages that share that. Rust is one of them, which is one of the reasons it fits so well into what we were trying to do. Java is another. Smalltalk is another. And these languages then allow you to not worry about the target platform. It goes everywhere. We did have to patch certain things. IEEE doesn't specify what happens with the low bits of transcendental functions. We had to patch that. Also, the random had to be patched because you need a replicated random. Random's used everywhere in multi-user systems, games, and that sort of thing. And why not Rust? Well, actually, that's a good question. Part of the reason was we started this project before Rust was really much of a thing. Rust would be actually an ideal platform. And we learned a lot working with Sebastian on the integrating Rapier into Croquet, and I'll show you a little bit about that. But everything that we can do in the JavaScript side, we can do in Rust. So it's really just a question of finding the resources to do that. And we feel like that's an obvious next step for us, among other things. Here's a demonstration of Croquet. This is 2 users. You notice I passed by one of them. Now I brought them both together, so they're actually, I'm controlling them both. But you see that little simulation is running. I pick it up and move it around. This is a multiplayer asteroids game, and everything is synchronized. This can be any devices, multiple devices. This is a multi-user text editor. I'm just saying that right there. And it's perfectly synchronized. So all these apps are written in Croquet. This is actually a live Bitcoin visualization. We're grabbing data from a Bitcoin service. This guy is really interesting. That flamingo is flying around. The code there says when actually I'm going to pause this. Oops, back up. Now I have to go find it. Sorry about that. Yeah, the code here, if you notice when you clicked on it, he paused. And so this code is really, this is live inside that system. This is a video here, but it was live in the system when you use it. And what's happening is we add an event listener and says pointer down, call the toggle function. Toggle function simply says, hey, if you're circling, stop circling. And then, so that's what's happening there. But I'm going to let it run again. And what you're going to see is we're going to, oops, we modified the code. I went too far. I want to back up just a little bit because that's pretty cool. I just thought that was just the coolest thing. So we're actually going to modify this code here. We're going to have notice it's multi-user, both sides, the editors being changed. And now we've got the flamingo flying backwards. We just changed the direction. This globe is another thing. We're actually grabbing all of the flights, all of the commercial airplanes in the sky at that moment and plotting them on this globe, so everybody sees all the airplanes. Those are, at the time, that every one of those dots was an airplane in the sky. Oops, I go back. Keep going. Oh yeah, I want to show you this. So we'll keep going here. Usually I do this live, but latency's kind of bad here. So now this is Portal. So I actually invented portals many years ago. So one of the users is going into the portal. Notice he changed into a cat, and he's looking around. But the portals are also kind of object that you can manipulate. You can drag them into a space. See, I'm moving it around. You can literally pick them up and drag them into another environment. They're just really just URLs. So they're just links. So that's one way to think about it. So I'm going to show you a couple of other demos. You notice that over there is a physics simulation. It's running on this computer here. And I have the same thing running on here on my PC. Now what's really interesting about this is that they're not communicating at all. We're basically, all we're doing is telling both of these what time it is, and that simulation is fully deterministic, so anything that happens on one happens on the other. But one of the things we can do is I can create a new object. I just created that sphere, and you notice the sphere happens in both. There's a green sphere. So that display is this computer. This display is that computer. This computer here, this computer and this and that are the same. So I can actually play around with that quite nicely. And by the way, this is my phone with exactly the same simulation. So I can tap on this, and you can see the same thing on everything. So I'm going to show you the next thing. I'm going to switch to this guy. So what's going on here is this is a game, a demo game that was developed by Brian Upton, who works with me. Brian was the game designer for Rainbow Six. What I'm going to do, actually, I'll show you anything I do one place. So you see me making this, I don't know if you can see it. You should be able to see me making a tower, both on that display and the big one here. So, and then I'm going to start generating a bunch of bots, like so. So all these bots are being generated on both. Let me make sure, yep, they're there. And what's really cool is everything is perfectly synchronized, but it's hard to tell because you see those little characters and you can kind of see them side by side. But what I'm going to do is I'm going to put a camera on one of them, and so I'll let that go. And sorry, so I just added a camera, and I'm going to add a camera to this guy too, and they should be synced. Whatever you see on one should be exactly the same as what you see on the other, I think. So even though we've got 500 bots in here, but there's no information being passed back and forth. We don't have to send any information back and forth because it's running deterministically. But at the same time, I can still interact with this world. So I can, you see, I'm kind of destroying the world in front of us as we move. I can just completely change everything dynamically. So it's a live world. It's not just, it's not just a simple, oh, well, it's a clockwork. It's far more interesting than that. So I'm going to show you another one. This is, oops, spelled G-O-S-I-M. No, G-O. There we go. So, oh, I spelled it wrong. Anyway, it doesn't matter. So what's going to happen is I wrote this game in about a week. And yeah, it's not as finished and amazing. But I'm going to have this guy join. And so it'll be, in a second, there'll be two of us. And you see there's two of us there. And this is actually a co-op defense game. So I'm going to shoot these guys and whatever. But what I'm going to do is I'm going to X, Y, Z, Z, Y, and then you. This is just a few of the bots, but I'm going to start generating many more. So we've got 12 bots out there, but I just made 1,000. There's 1,000 bots coming out at us. It's probably behind me here. Yeah, there they are. And you can see that. So we've got 1,000 bots, all perfectly synchronized. And I'm going to prove that to you. I'm going to go to top view. So you see both of those are exactly the same. But I can still interact with them. I can still shoot them, although there are way, way too many for me to fight off right here. But you get the idea is we're able to share very, very, very complex worlds together at the same time. Here's some more coming over the side, and I'll switch over and, oops, take them out. And notice, by the way, the missiles bounce off, and they bounce off in exactly the same way on both. Everything is perfectly synchronized. Oh, somebody's driving that. That's somebody joined me. Cool. Anyway, so you get the idea. Notice I'm running on a pretty fast VPN. If you're running this, you'll probably see a lot of latency otherwise. Okay, let's keep going. I'm going back to that. That's the demos. I'm going to talk now a little bit about how Croquet is different from traditional client-server architectures, and then I'll go into deeper dives on things. So traditional model is on the left-hand side, where you have a server, and then you have the view, the client. The server's on the internet side, so it's maybe at some sort of cloud or something, and the view is on your machine. So when you're playing multi-user, the server is the source of truth, and then what you see is basically the server saying, hey, this is what happened. The problem with that is you see the big black arrows coming down. There's a huge amount of data that has to be passed from the server to the view to the client. And not only that, but it's a very disruptive kind of thing because basically you can do predictive models of what might happen, but the server is going to say, no, that didn't happen, this is what happened. Croquet is very different. It has a completely different architecture, and one way to think about it is we're moving the server from the internet side down onto the client. That shared bit identical single logical computer, as Alan Kay talks about it, is a shared virtual computer that's running bit identical without having to communicate, as I said. And I'm going to talk a little bit about that, of how that works in a sec. Now, this is a model view controller architecture, if you're familiar with those. The model in this case is that virtual computer. The view controller is the thing that renders, and it's the thing that allows you to interact. So you click on something, that's a controller. When you watch something, that's the view. But the intelligence, the AIs, everything that drives that world forward is in that virtual computer and that shared state. So the model is a single, as I said, a single logical computer, and views interpretation of that model. So here's a number of nice features of Croquet that why we like it and why we think you should check it out anyway. It's decentralized. It's decentralized at almost every layer, and the intent will be it's decentralized everywhere, top to bottom. So as I said, clients perform replicated bit identical computations. It's synchronized, as you saw. Events are replicated. So when I click on something, that message goes up to the reflector and is shared. I'm going to go into a little bit more about that. One of the things that's really important, and you saw that with the game, was that you can join in the middle anytime. Doesn't matter when. And what's really nice is the programmer doesn't have to worry about that. It just works. So this is literally, it's a kind of a micro operating system. I think Randy Farmer described it as a collaborative microkernel. It's very low latency. One of the reasons is we can put reflectors. Reflectors themselves don't have any application state at all. That means you can move them anywhere you want to, and you can make them very, very close to the game players, which means that one part of it, the latency drops because it's just closer, but the other reason is we spend no time in the reflector. There's no compute there. This makes it even easier to make a fully decentralized system. Notice it was cross-platform. I showed it on my phone. I showed it on these two guys. Usually I show it on a Windows device. It's persistent. If we leave this game right now and come back, we can come back later and pick up right where we left off. And it's secure. All messages are end-to-end encrypted so that even the reflector can't look at the messages. So you can't attack the system from the cloud. Reflectors are very tiny. You can run them on a Raspberry Pi, actually. Stateless, very secure, encrypted end-to-end. Our goal is sub 15 milliseconds everywhere. And we think that might be achievable. We know 15 to 30 is doable. Currently, we're worldwide on Google Cloud, and we've also deployed within corporate firewalls on Raspberry Pis. We've also deployed on Cloudflare Durable Objects, Verizon on their 5G MEX via AWS Wavelength. I'll talk a little bit about where we're going next after that. So this is worldwide, every place except China right now. So we want to change that. So synchronized events. This is kind of a deeper dive into the system and how it works. So I'm going to talk about kind of that. I showed you what it does, but this is where it gets really interesting. So the edge reflector, as I mentioned, has no state. The Croquet kernel is those identical virtual machines, that single logical computer. And the view is what you see and what you interact with, the view controller. It's locally rendered. And notice the gray area is the client side. The white area above is the internet. So, traditionally, we think of it as a server and a client, but that's not the way Croquet works. The OS can be considered the reflector plus these virtual computers together. That one without the other is meaningless. So you have to think of it in those terms. And then, of course, the view is what you see, that's traditional. So what's going to happen is the user is going to interact with that view. He clicks on that, let's say in some way, like I did when you hit the space bar in the game or whatever. What happens is we generate an event. That event is then triggers, gets into the edge reflector. Edge reflector creates a timestamp and redistributes that to all the virtual computers that are in that session. They get that message, and basically they do a computation of that, but actually all the previous queued up messages that might already exist. So this is one of the magic things about how Croquet works. You can send a message to yourself in the future that gets put into an internal queue inside that virtual computer. There's a number of reasons you want that. One is obviously you're saying to yourself, turn 10 degrees in 10 milliseconds as an example. But the other thing is that queue of upcoming events is one of the things that gets persisted, gets saved. So when a new user joins, they can take that same they can take that same virtual machine, and it includes not just the instantaneous state, what's happening right now. It also has all the information about what's about to happen. So the update's sent to the view, and the view is updated, and the worlds are perfectly synced. So I mentioned dynamic joining. I'm going to talk a little bit about that real quick. So you notice when I started to play this Guardians game, the tank game, we started out with a single user. It's like this, and we're doing whatever we do. But one of the things we do about every 5 seconds of compute time, which isn't the same as real time, we take a snapshot of that virtual computer. So when my second computer joined the game, we also save all the messages that may have occurred from the user. So if I was hitting the space bar really fast and we made a snapshot, we might have made a snapshot before all those messages got sent. And so to update a new user, what they have to do is grab that virtual computer and play back the messages they would have missed that weren't part of that computation. So the first thing we do is copy that archived virtual computer state into into the other user's virtual machine. He generates a view, and then we play back the messages that they missed, and now they're synced. That's how it works. Okay, and snapshots, every snapshot is defined almost exclusively by external event, compute, external event, compute, external event, compute, external event, compute. And what that means is the end state is something we can snapshot and save. What's nice is not only can it be used by the new user joining while the system's running, but it's also persistent in that if all of us leave and come back, you can join exactly where you left off. You don't miss anything. You don't miss a single event. So I'm going to do a bit of a deeper dive. Let me just check the time because it's 2:28. So I got about 20 minutes to kind of review some additional ideas here. And I'm going to do this. So everything I'm showing you is available in open source. One of the things we've recently built is Croquet for Unity. And we're really, really happy with it. It's still, it's in its final beta. It's basically at a golden master at this point. But it allows you to build very, very high quality games using Croquet. And Unity has a very, very fast rendering engine. So the Guardians app actually, I showed you the web version, and we also have a fully implemented Unity version, which you can download and get access to all the sources and play with it. We have a number of other apps. I already talked about this. I'm going to talk about a few key ideas here. I mentioned this idea that we actually have an internal queue. When you have this virtual machine, we have an internal queue of all the future messages. And in fact, that's how you do it. We say, do something here. This.future100, do something. This is kind of a little trick that we learned. This is, I could call it temporal tail recursion. So what's going on is we do something, we execute some code, and then we say, hey, I want to do it again in 100 milliseconds. So what we do is we call it this.future. This is JavaScript, by the way, so if you're familiar with that, if you're not, I'm pretty sure Rust isn't that different. This.future100, do something. And what it does is puts that message into a sorted queue, sorted by time, of course. And so when it executes, it's going to call the do something function again, which is also going to put itself back into it. So this is how you do kind of an infinite loop in time. We also use a publish subscribe model. The reason is, so we have the model in view. In JavaScript, the view can actually read from the model. You never want to write into the model for a very good reason, which is if you did, you would break the consistency. Basically, you'd have the system diverge. So whenever you want to write something into the model from the view, when you click on something, what you want to do is publish that event. That event then goes via the reflector. Reflector puts that timestamp on, redistributes it, and everybody now has that same exact event at the same virtual time. So publish is a real key thing. And of course, on the other side, we do a subscribe to listen to that. I'm going to keep going. Say listen is a shorthand version of that. We have an entity component model where you can just do a say listen. This object is connected to this object on the model view side. It's just a shorthand for managing that. I'm going to skip all this. No, we have on the Unity side, and actually on the JavaScript side, a number of tutorials. I'm just going to jump through these, just kind of give you a sense. This takes you right through everything you need to know to do the Unity application. So we've got a number of tutorials that I want to just talk about briefly. This is a simple one. You're just using the keyboard to move your block left and right. And this is the code. This is all you need. One thing to note, and you probably saw this earlier, there's no netcode here. You don't need it. Since we're running a bit identical shared simulation, you do not need to specifically say, send this message. We do have the subscribe, and that's just listening to those transformations of state. And you do a publish, but it's really just communication between the model and the view. You don't have to think about it in terms of, I'm sending a message out there, is it going to arrive? I'm sending a message out there, does that trigger something else that's going to send a message that, in other words, there's no race conditions. It's a well-defined executable. And next is this guy where we do parent-child relationships. Not much different, actually. There's a little bit of extra code for defining a child with a spin. This one is just that. We're spinning the objects around. It's basically, step of creating almost anything you can do a multi-user. But one of the things to notice is there's almost no code. To give you an idea, the entire Guardians game for all the logic is about 500 lines of code for everything you saw there. So you can create much smaller applications that do much more this way. This is creating objects, clicking on them, and they kind of balloon up, and then they kill themselves. Anyway, all this document's available online. If you go to croquet.io and the Unity side of it, you'll find every bit of this. All these demonstrations are available for you to play with. So this is a simple avatar application. And then I'm going to go a little further. This is obviously using Rapier. This is the demolition project that we did. We've been working with Sebastian for a few years now, and it's just thrilling, how easy it is to build this kind of application, and it's multi-user. Everything you see here works perfectly synchronized. So thank you, Sebastian. And then this is the Guardians app, and again, all the source code for that's available, and everything's there for you. So I'm going to switch back to a few, just talk a little bit about what's next. First thing is we're converting the system, we're making it fully decentralized. If you know what a decentralized physical infrastructure, what we're doing is taking our reflectors, and if you're familiar with IPFS, Interplanetary File System, where anybody can host a part of it, we're going to allow anyone to host a reflector or reflectors, and then in return for that, and of course it'll be all open source, in return to that, for the hosting reflectors, you'll get paid tokens for that. So our current deployment looks kind of like this. We're actually a broader footprint than this. But once we deploy the reflector network, then what happens is two things. One is the cost of using this multi-user platform drops dramatically a lot. And the other thing is the deployment goes way up, which, as I said before, our goal is sub 15 millisecond latencies everywhere. And if you do multiplayer, you understand that that's crazy. But we think it's quite doable with this approach. The other thing we're doing is, and this will be sometime next year, I think. Currently, when the first user joins, we find the reflector close to them, which means that the other users are at something of a disadvantage if they're far away. So for example, if I join in North Carolina to reflector, I'm going to find either one, South Carolina or Richmond or something like that. And if I then choose to connect to somebody in Hong Kong, their latency is going to be on the order of 160 milliseconds, where mine is going to be 15. And so what you need is a way of managing that. And of course, you don't want to, punish the guy who's close by, but you also want to have a vehicle to make the other people a little bit better, a little more competitive, if that's what it is. Or if it's a multi-user application, they're doing a lot of work. So what happens is we have reflectors over there, and we can actually dynamically switch reflectors. We can do that, we believe we can do that in just a few milliseconds, and no one will notice. So that's the other thing that we've been working on. And that is the end.